Hello everyone. We have been discussing about quantum mechanics and we have given a short introduction for quantum mechanics in the last class, and today we'll be discussing about blackbody radiation. Okay, I told you that there were many problems which cannot be solved using classical physics. This is the first problem which was not solved using classical physics, and that is blackbody radiation or thermal radiation. Okay, they are both the same. Okay, so you might be wondering what is this black body radiation or what is this thermal radiation. In simple terms, I can explain that in simple terms. If you just heat an object, for example, an iron piece, okay, if you heat that iron piece, it will eventually turn into red color. Okay, if you give more heat, it will be turning into yellow color, and if you give more heat, it will be turning into white color. Okay, means there is a change in color with the application of or with the increasing in temperature. Okay, and because of that it is emitting a kind of radiation. Okay, and because of the change in frequency it is appearing in red color, then yellow color, then white color. Okay, that is simply black body radiation, or that is simply thermal radiation. Okay, black body radiation is an ideal case. We can say thermal radiation. Okay, so in simple terms, what is thermal radiation? If an object is heated, it will emit some radiation. That radiation is thermal radiation. The radiation caused due to heat, thermal. Okay, that is simply that. Okay, so as I told you, when they observe the spectrum of this thermal radiation, there is a continuous distribution of frequency from infrared to UV. Okay, and they studied the emitted radiation from thermal bodies, from hot bodies, and in their study they found that the emitted radiation from hot bodies has a frequency ranging from infrared to UV in a continuous basis. Okay, they couldn't explain this continuous nature of radiation emitted by hot bodies using classical physics. Okay, and opposed to that, if we heat a gases, okay, we know about the spectrum of gas particles. Okay, this spectrum of gas is discrete, and the spectrum of solid materials when heated is continuous. Okay, they are ranging from infrared to UV. That is the observation. Okay, so normally in normal this room temperature also objects are emitting radiations, but we cannot see that because of the difference in frequency. Okay, we can see things only in the visible range, that is 400 nanometer to 700 nanometer. Okay, if an iron piece is kept in the sunlight, it is also radiating some radiations. Okay, we cannot see that because it is not in the visible range. Okay, so that is thermal radiation. Okay, so the problem lies on explaining the continuous nature of frequency emitted by this hot bodies. That is the question we have to answer. Why is that continuous spectrum, or what is the energy density of that radiation? That is our problem. Okay, so the basic problem here is why it has a continuous nature, or in other terms it can be explained as we are heating an object, we are heating an iron piece and it is emitting radiation. An iron piece is a matter and that is radiation coming out, so it is the interaction between matter and radiation. Okay, so basically this consists of energy exchange between matter and radiation. Okay, this is basically the energy exchange between matter and radiation. Okay, so this is our problem, and it was difficult to study the spectrum of hot bodies. Okay, so heating an iron piece and studying about the thermal radiation emitted from that, it is a difficult task. So they imagined about a similar situation. You have to understand this. Okay, if we heat an iron piece and then radiations are emitted, so we have to take that into the lab and study about that. It is difficult process. Okay, so they substituted that problem with an equivalent counterpart. Okay, that is actually a black body. Okay, to study hot bodies is difficult, so they obtained a similar situation which is known as black body. So ideally, what is a black body? A black body is an object which can absorb all radiation. Okay, all kind of frequency or all wavelength can be absorbed using that light. Okay, that is an idealized black body. An idealized black body absorbs all radiation Okay, and it appears black when illuminated. Okay, if we blow some light on that, it will be appearing as dark in color. Okay, now because it is absorbing all radiation. Okay, now it emits all radiation when heated. When we heat that object, it will emit all radiations. Okay, that is the difference. Okay, so what causes this emission of radiation? When we heat an object, we are giving thermal energy. Okay, we are giving heat energy. Okay, and this causes the electrons to attain heat energy. And when they obtain heat energy, they will be agitating. That is thermal agitation, or that they will be vibrating. Okay, these vibrations causes the production of electromagnetic radiation. You must have studied that in the electromagnetic theory. Okay, simply when an electron is continuously oscillating, it will cause the production of electromagnetic radiation. Okay, that is the physics underlying here. Okay, so now we have to study about this radiation. For that we have chosen black body, and there is no ideal black body. Okay, an object which can absorb all radiation, and when it is heated it emits all radiation. That is an ideal case. Okay, it is an ideal case, it is not practically possible. So in order to study that practically, we are assuming a practical black body. Okay, what is a practical black body? In a lab, a black body can be obtained by making a metallic box. Okay, a completely polished metallic box, polished in the inside. So a practical black body is a metallic box which is completely polished from the inside. Okay, with a small hole. Okay, with a small hole on one of the sides. Okay, so what happens is that when electromagnetic radiation enters through the hole, it will undergo multiple reflections inside the box. Okay, because the inside part is completely polished. Okay, so when a radiation enters inside, it will be undergoing multiple reflections and it will be trapped inside the box. So that means it is absorbing the radiation. When a radiation enters the box, it cannot exit. So that is complete absorption. Okay, so that can be compared to a black body. Okay, it can absorb all radiations. Okay, whatever the frequency is, it will be trapped inside the box. So that is an ideal absorption. Okay, on the other hand, if we give some heat, if we heat this box, it will undergo thermal heating. Okay, so heating the box means the electrons in the walls gets heat energy and they will start vibrating, and that causes the emission of radiation, and after multiple reflections that radiations will be coming out of the hole, and eventually the hole will begin to glow. The hole will be glowing. The hole is glowing means radiation is emitting. Okay, so when radiation enters the box, it is trapped, and when it is heated, radiations are emitted. So this can be compared to an ideal situation. And one of important point is that it is not the box that is the black body. This box is not the black body. This hole is the black body. Okay, this hole is acting as the black body. Okay, it is an important point. Okay, now we have to analyze the spectral distribution of the radiation coming out through this hole. Okay, we have to analyze the spectral distribution of radiations coming out through the hole. Okay, that is our task. Okay, so after the invention, after knowing this problem, many scientists studied about the problem. Okay, and they concluded some results. Okay, so first of all, we will be discussing the observations on black body, not the explanation, observation. Okay, what they observed about black body radiation. The first observation is that energy density shows a maximum at a given frequency which increases with the frequency. Okay, the main or the important part about this black body radiation is its graph itself. Okay, we have to explain this graph. Okay, what is this graph about? It is energy density. Energy density is represented by U of nu. U of nu. U of nu is nothing but energy density. Okay, energy per unit volume in the radiation. Okay, that is energy density, U of nu. U of nu versus nu. Okay, what will be the shape of this graph? Okay, so I can tell you this. The shape of this graph is like this. Okay, it will be round like this. Okay, kind of this shape. You can refer any standard textbooks for the exact graph. Okay, this is at a particular temperature, say T1. Okay, this graph is showing for a particular temperature T1. Okay, this will be the energy density versus frequency graph. And it is important, when we increase the temperature, this peak is shifted to the right. Okay, so it will be somewhat like this. Okay, so this temperature is T2. This is for a temperature T2, and it is obvious that T2 greater than T1. Okay, T2 greater than T1. Okay, T2 greater than T1. Okay, now if we again increase the temperature, the frequency shifts again to the right. Okay, this is temperature T3, and T3 is greater than T2 greater than T1. Okay, that means with the increase in frequency, with the increase in temperature, this particular peak is shifting to the right. Okay, this frequency is shifting to the right. Corresponding to a temperature, there is a frequency. Okay, this frequency is nu1. Okay, corresponding to temperature T2, there is a frequency nu2. Corresponding to T3, there is a frequency nu3. Okay, this is the case. Okay. Now, what if we draw a graph between energy density and wavelength? Energy density and wavelength. The graph shows a similar structure, but it is different. Okay, at a temperature say T1, the graph is like this. Okay, this temperature is corresponding to lambda 1. Okay, if we increase the temperature, the shift is to the left. Okay, the shape will be like this. Okay, so this temperature is T2. Okay, T2 greater than T1. Okay, if we again increase the temperature, then that graph shift to the left like this. Okay, T3. Note that here also T3 is greater than T2 is greater than T1. Okay, so this is the point. So corresponding to a particular temperature, there is a peak in the energy density. Okay, corresponding to a particular temperature, there is a peak in the graph. These are the peaks. Okay, these are the peaks. Okay, whatever the graph is, these are the peaks. Okay, and that particular wavelength, I'll call it as lambda max. What will I call it? Lambda max. Okay, what is lambda max? The wavelength corresponding to the maximum energy density at a given temperature. You should note down that. Okay, the wavelength corresponding to the maximum wavelength at a particular temperature. Sorry, the wavelength corresponding to the maximum energy density. Okay, the wavelength corresponding to the maximum energy density at a given temperature is called lambda max. Okay, so for temperature T3, lambda max is this. Okay, and for temperature T2, the maximum energy density is at this point. Okay, the wavelength corresponding to that point is called lambda max in the second case. For temperature T2, lambda max is this. Okay, and for temperature T1, lambda max is this. Okay, similarly, if lambda is max, then nu will be minimum. Okay, so I can call this nu min. Okay, corresponding to highest energy density, there corresponds a frequency. Okay, so our focus is on the lambda max. We'll be discussing in terms of lambda. Okay, this is the graph. Hope you understand the graph completely. If you have any doubt regarding this graph, you can comment. I'll explain again. Okay, that's it. For my satisfaction, I'll explain that graph once more. Okay, this is frequency versus energy density. Okay, so let's say this is temperature some 500 Kelvin. Okay, for 500 Kelvin, the maximum energy density is this. Okay, and the corresponding frequency is this. Okay, if we increase the temperature to 1000 Kelvin, then the graph will shift to the right. Okay, this is the maximum energy density. This is the corresponding frequency. Okay, if we again increase the temperature to some say 2000 Kelvin, the graph again shifts to the right. Okay, this is the frequency versus energy density graph. Okay, now what about the energy density versus wavelength graph? Okay, so it is like this. This is for a particular temperature 500 Kelvin. Okay, for 500 Kelvin, this is lambda max. Okay, this is the maximum energy density of this particular graph. Okay, and if we increase the temperature to some 1000 Kelvin, the graph will be shifted to the peak will be shifted to the left. Okay, so this is the maximum energy density and this will be the corresponding lambda max. If we again increase the temperature to 1500 Kelvin, peak is shifted to the left again. This is lambda max. And again at 2000 Kelvin, this will be the corresponding maximum wavelength. Okay, this is one observation regarding black body. Okay, so from this it is clear what is the reason behind change in color. When an object is heated, it is changing from red to yellow to white. This question itself is asked in many exams. What is the order of change in color? It is first red, then yellow, then white. That is the order of change in color for a thermal body. Okay, so corresponding to this lambda, it will show a color. Okay, when wavelength changes, it will show another color. Okay, for example, if it is 400 nanometer, it will be some violet. Okay, if it is ranging to 700 nanometer, it will be red in color. Okay, and corresponding to 600, it will be some Vibgyor, you know. Okay, Vibgyor. Okay, this is ranging from 400 to 700. Okay, based on the value of wavelength, the color will be different. Okay, that is the reason behind change in temperature of a black body. Hope it's clear now. Okay. Now, based on this observation, okay, Wiens proposed a law called Wiens displacement law. Okay, this is a fact about thermal radiation. Okay, this is not a explanation. Okay, this is not an explanation. This is an existing fact about blackbody radiation. Okay, what we observed, if we compare the energy density and wavelength, the graph shows like this. Okay, this will be corresponding to T1 and this will be the peak corresponding to T2. Okay, that means from this we understood that corresponding to the maximum energy density, there is a wavelength called lambda max. Okay, what is lambda max? It is not the maximum wavelength present in the radiation, but it is the wavelength corresponding to the maximum energy density. Okay, this is maximum wavelength. Okay, but this is lambda max. What is lambda max? It is the wavelength corresponding to maximum energy density. Okay, not the maximum wavelength in the radiation. Okay, and corresponding to this particular temperature, the maximum energy density is this. Okay, and it is this is the corresponding lambda max. Okay, so from this it is clear that lambda max, when the temperature increases, lambda shift to the left. That means lambda max decreases. Okay, so we can say that lambda max is proportional to 1 by T. Okay, or lambda max is inversely proportional to the temperature. From this we can say that lambda max into T is a constant. Okay, and that constant is 2.898 into 10 raised to minus 3 meter Kelvin. Lambda and temperature, lambda meter, T temperature, Kelvin. Okay, this is called Wiens displacement law. Why is this displacement included in the law? Displacement means when the temperature increases, wavelength displaces to the left. That is the reason we are saying it as Wiens displacement law. So what is Wiens displacement law? When the temperature increases, maximum wavelength corresponding to the maximum energy density decreases. Okay, that is lambda max into T is a constant. This constant is important. This will be helpful in solving many numerical problems. Okay, lambda max into T is a constant. That is 2.89 into 10 raised to minus 3 meter Kelvin. Okay, now we have to discuss about this Stefan-Boltzmann law. Okay, this Stefan-Boltzmann law. Okay, so in 1879, Stefan and Boltzmann concluded that the intensity, what is intensity? Power per unit area. Okay, the intensity of a blackbody radiation is proportional to the fourth power of temperature. Okay, the intensity of the radiation emitted by a blackbody is proportional to the fourth power of temperature. Okay, so I can write intensity is equal to some A sigma T raised to 4. A sigma is the proportionality constant. Okay, here A is called emissivity. A is called emissivity, and the value of emissivity is equal to 1 for a black body. 1 for a black body. Okay, and for the other particles it is less than 1. Okay, lies between 0 and 1. Okay, for most of the problems we will be treating this as 1. Okay, so in simple terms, Stefan Boltzmann law is I equal to sigma T raised to 4. Okay, and sigma is Stefan Boltzmann constant. Stefan Boltzmann constant. Okay, its value is very important. It is 5.67 into 10 raised to minus 8. Okay, watt per meter square Kelvin raised to 4. Okay, that is the value of Stefan Boltzmann constant. Okay, this value is also important for solving numerical problems. Okay, 5.67 raised to minus 8 watt per meter square Kelvin raised to 4. Okay, so these are the two observations of blackbody radiations. Okay, these are the two laws about blackbody radiation. Okay, now we have to explain blackbody radiation. Okay, we have to explain this distribution, or in short, we have to obtain a formula to fit this data. Okay, we have to obtain a formula to fit this data. For example, we know the graph of sin x is like this. So what is this formula? F equal to sin x. Okay, this formula can explain the graph. Similarly, we have to obtain an expression to explain this graph. Okay, so we have to obtain what? U of nu. Okay, U of nu equal to something and something. We have to obtain that formula. And first of all, two scientists came to explain that, and that both were based on classical physics, and that were both a failure. Later on, Planck explained that. We'll be discussing that now. Okay, now we have to study how they tried to explain blackbody radiation. Okay, we have to obtain the curve between energy density and frequency. We have to obtain an equation to explain that curve. That is our aim. Okay, many scientists came to explain that. First among them was Wiens. Okay, using thermodynamic arguments and using Stefan Boltzmann law, Wiens obtained a formula for energy density distribution, and that is called Wiens energy density distribution. Okay, and it is given by U of nu t is equal to a nu cube e raised to minus beta nu by t. Okay, here a and beta are some empirically defined parameters or constants. They can be varied to fit the data correctly. Okay, so Wiens was the first to explain blackbody radiation, but it was not successful. Why it was not successful means it works only at high frequencies. Okay, we know how is the shape of that graph. Okay, this Wiens energy density distribution formula works only at high frequencies. Okay, that means the graph shown was like this. Okay, how is our graph? Our original graph is like this. Okay, like this. Okay, and Wiens law worked only in this particular region. That means high frequency. For lower frequency or mid-range frequencies, Wiens law was not successful. Okay, the curve was different using this formula. Okay, so in short, Wiens law works only at high frequency data. Okay, now secondly, there came Rayleigh. Okay, Rayleigh and Jeans. They were both they were two scientists. Okay, Rayleigh and Jeans. Okay, they tried to explain blackbody radiation using a different formulation. And what is that? Rayleigh and Jeans considered radiation inside the box as standing waves. What do you mean by standing waves? Standing waves means the nodes of the waves were occurring at the walls of the surfaces like this. They were forming standing waves, right? This crust or trough appears at the walls of the box, so that they will be forming standing waves. Okay, so Rayleigh and Jeans considered these radiations as standing waves. Okay, the radiation inside the cavity is full of standing waves. Okay, and how they devised a formula is like this. They found a formula for energy density. U of nu t is equal to number of standing waves into average energy. Okay, somehow they have to calculate the total number of standing waves. Okay, they have to find the total number of standing waves inside the cavity, and then after that they have to multiply that with the average energy. Okay, if there are 10 standing waves, and if we multiply that with the energy of one standing wave, we will get the total energy. Okay, that is the formula. Okay, so total energy density U of nu t is equal to number of standing waves into average energy. Number of standing waves into average energy. Okay, that means U of nu t is equal to N of nu into average energy. Okay, and they obtained number of standing waves using the formula N of nu is equal to 8 pi nu square by c cube. Derivation is not important. Okay, and this formula is correct. Okay, N of nu is equal to 8 pi nu square by c cube. What is this? Number of standing waves in the frequency range nu to nu plus d nu. In between nu and nu plus d nu, the total number of waves is 8 pi nu square by c cube. Okay, and using classical equipartition theory, they obtained the average energy as like this. Okay, average energy is equal to integral 0 to infinity E into e raised to minus e by kt dE divided by integral 0 to infinity e raised to minus e by kt dE, and they obtained it as kt. If you solve this integration, we will be obtaining kt. Okay, this is similar to Laplace transform equations. Okay, so we'll get kt. Therefore, we obtained N of nu and we obtained average E, and therefore the total energy is 8 pi nu square by c cube into kt. What is this k? It is Boltzmann constant, 1.38 into 10 raised to minus 23 joule per Kelvin. Okay, so this is how Rayleigh formulated the energy density, and unfortunately their experimental data fits at lower frequencies only. Okay, the graph corresponding to this particular equation was like this. Okay, it was like this. Okay, and how is our original graph? It is going like this. Okay, so that means this is Rayleigh's graph. Okay, so it works only at low frequencies. Okay, this is frequency graph, this is energy density, and this works only at low frequency data. And there was another problem associated with this Rayleigh's formula. It is called ultraviolet catastrophe. What is this ultraviolet catastrophe? It means when the frequency tends to higher values. From this equation it is clear that energy density is proportional to square of frequency. When the frequency increases, energy increases as a square. Okay, so when the frequency tends to infinity, the energy density tends to infinity. That means energy density is tending to infinity, means the box is containing infinite amount of energy, and that is not possible. If a box contains infinite amount of energy, we can make everything possible, right? Using that energy we can do many things as we want. Okay, that is not possible. Okay, they obtain that when the frequency tends to infinity, the box contained infinite amount of energy. Okay, that frequency corresponding to higher frequency is called UV. It comes in the UV range of the spectra. Okay, so it is a catastrophe. Catastrophe means something which is not possible. In Malayalam we can say Virodhabasam. Okay, that is called UV catastrophe. Okay, so that was the problem associated with Rayleigh's formula. Okay, now we have to discuss Planck's formulation. Okay, now we have to discuss Planck's radiation formula. Okay, so Planck's energy density distribution. Okay, so here is how he formulated the problem. Okay, the energy density formula is the same. That is, energy density is equal to N of nu into average energy, and that N of nu, that means number of standing waves in the interval nu and nu plus d nu, is the same 8 pi nu square by c cube. Okay, but the calculation of average energy is different. Okay, religions used classical equipartition theory, and in that theory, the energy exchange between matter and radiation is continuous. That means any amount of energy can be exchanged between matter and radiation according to classical theory. Okay, that is how we calculated the average energy as kT. Okay, but here Planck used a different formulation. Okay, he told that the energy exchange between matter and radiation must be discrete. It cannot be continuous, it must be discrete. You should recall the continuously flowing water and drop by drop water. Okay, that is continuous and discrete. Okay, so Planck told that energy exchange must be discrete. Okay, the energy of radiation from the oscillator must come in integral multiples of h nu. Okay, what is this oscillator? The frequency of oscillator and frequency of radiation are both the same. Okay, when we heat the box, electrons will be vibrating with a frequency nu, and corresponding to that frequency nu, with the same frequency nu, radiations will be emitted. That means the frequency of oscillator and frequency of radiation both are same. Okay, so Planck told that the energy of radiation from the oscillator must come in integral multiple of h nu. That means energy is equal to nh nu. Okay, not h nu. Energy is equal to nh nu, where n equal to 0, 1, 2, 3, etc. And this h is called Planck's constant. Its value is 6.626 into 10 raised to minus 34 joule second. Okay, that is how he formulated. And now religions use the formula this to calculate the average energy. That means average energy is equal to integral 0 to infinity e raised to minus e by kt dE by integral 0 to infinity e raised to minus e by kt dE. Okay, he used the same formula, but since this is discrete, it is not continuous. Okay, integration is for continuous basis. Okay, for discrete basis, we have to change this integration to summation. Okay, so instead of this integration, Planck used summation. Okay, and for this energy E, he substituted nh nu. That means sum over n equal to 0 to infinity nh nu e raised to minus nh nu by kt by sum over n equal to infinity e raised to minus nh nu by kt. And solving this, he obtained average energy as h nu by e raised to h nu by kt minus 1. This is very important. Okay, so the total energy density U of nu T is equal to 8 pi nu square by C cube into h nu by e raised to h nu by kt minus 1. Okay, this is how he obtained the formula, and this is called Planck's radiation formula or Planck's energy density distribution. Okay, this was exactly matching the experimental observation. Okay, using this graph, he obtained the exact graph like this. Okay, and in terms of wavelength, it can be written as U of lambda T is equal to 8 pi hc by lambda raised to 5 into 1 by e raised to hc by lambda kt minus 1. Okay, in most of the problems, we will be using this formula. Okay, that's it. Okay, so he obtained the graph exactly. Okay, this was in agreement with the experimental observations. Okay, now there will be in graduate courses, there will be question asked to compare the three laws. Okay, so this is Religion's formula. Okay, and this is Wien's law, Wien's formula. Okay, Wien's energy density distribution, and this is Planck's formula. Okay, so this is Planck's formula, which is the exact formula required to explain blackbody radiation, and the other two are Religion's formula and Wien's formula. Okay, now there is one more thing. Okay, this is the last one more thing. At Religion's formula works at low frequency. This Religion's formula can be obtained from Planck's law. Okay, low frequency means h nu much less than kt. Low frequency means h nu much less than kt. Okay, okay, low frequency h nu is less than kt. Okay, so I can write h nu by kt is much less than 1. Okay, that means h nu by kt is much smaller. Okay, therefore I can write e raised to x is equal to, what is the formula for e raised to x? When x is small, it can be estimated to 1 plus x. When x is small, e raised to x is equal to 1 plus x. Similarly, e raised to h nu by kt will be equal to 1 plus h nu by kt when h nu by kt is small. Therefore, at low frequency, u of nu comma t is equal to 8 pi nu square by c cube into h nu by e raised to h nu by kt can be written as 1 plus h nu by kt, 1 plus h nu by kt minus 1. Okay, this 1 and 1 cancels. Okay, h nu and h nu cancels, and what will be left? 8 pi nu square by c cube into this kt goes upside, it will be kt. This is nothing but Rayleigh's formula. Okay, and this is how he obtained Rayleigh's formula. Means Rayleigh's formula is working at low frequencies, and Wien's law can also be obtained from this formula. Okay, with a similar approximation, when h nu is much greater than kt, we can obtain Wien's distribution. Okay, so this is how Planck explained this thermal radiation successfully. Okay, he obtained the exact graph. Okay, this is all about blackbody radiation or thermal radiation. In the next class onwards, we will be discussing complete problems on blackbody radiation. Okay, all numerical problems. We'll be discussing each and every one. Okay, see you in the next class. Thank you all.